Welcome back, students. In today's video, I'll start chapter 9, which is hydrogen. Hydrogen has the simplest atomic structure of all elements that are found in nature. In atomic form, hydrogen consists of one proton and one electron. Clear? However, in elemental form, it exists as a diatomic molecule, that is H2, and this is called dihydrogen. Clear? And students, this is for your general knowledge. It is hydrogen that forms more compounds than any other element in the periodic table. Hydrogen was first discovered by Henry Cavendish in the year 1766. It was Lavoisier who proposed hydrogen its name. Clear? Why? Because hydrogen produced water on burning with oxygen. For this reason, he gave hydrogen its name. Okay, this is based on two Greek words, hydro and gene. Hydro stands for water and gene stands for producer. Clear? Now, the chemical symbol of hydrogen is H. Its atomic number is 1 and we know its electronic configuration is 1s1. Now we move on to the next important topic, which is position of hydrogen in the periodic table. Students, this is a very important topic in this chapter and surely you can expect this question in your exam. Hydrogen holds a unique position in the periodic table. Clear? It is the first element in the periodic table, and hydrogen, you will find that it resembles alkali metals, which are group 1 metals, and halogens, which belong to group 17 in many of its properties. Now let us see how hydrogen resembles alkali metals and halogens in its properties. The electronic configuration of hydrogen is 1s1. And what is the outer electronic configuration of group 1 elements? It is ns1. For this reason, the outer electronic configuration of hydrogen is similar to the outer electronic configuration of alkali metals. Clear? We know halogens are one electron short of achieving the electronic configuration of their nearest noble gas. We know the electronic configuration of hydrogen is 1s1. If it had one more electron, then it would have had the electronic configuration of its nearest noble gas helium, which is 1s2. So like halogens, hydrogen is one electron short of its nearest noble gas configuration of helium. Okay, that is 1s2. Alkali metals have one electron in their outermost shell, and they tend to lose this outermost electron easily in order to achieve the octet configuration in their outermost shell. Like alkali metals, since hydrogen also has only one electron in its shell, it can also lose its one electron and become a unipositive ion like this. Clear? Since halogens are one electron short of achieving the electronic configuration of their nearest noble gas, they exhibit greater tendency to gain an electron. Clear? Only then they can have the electronic configuration of their nearest noble gas. Like halogens, hydrogen also shows greater tendency to gain an electron and achieve the electronic configuration of helium. Now, when hydrogen gains an electron, it forms a uninegative ion like this. Remember, when I taught you chapter 3, I told you that oxidation state of an atom of an element tells you about the number of electrons that can be lost, gained, or shared by an atom of an element when it involves in chemical bonding. Since alkali metals lose their outermost electron, they have an oxidation state of +1, and hydrogen has only one electron, and when it loses this electron and resembles alkali metals, it also exhibits an oxidation state of +1 in majority of its compounds. We know halogens show greater tendency to gain an electron. Clear? So they have an oxidation state of -1. Since hydrogen also has greater tendency to gain an electron like halogens, it also exhibits an oxidation state of -1 in some of its compounds. Like alkali metals, hydrogen reacts with electronegative elements like halogens, oxygen, sulfur, etc. to form binary compounds like halides, oxides, sulfides, etc. Like halogens, hydrogen combines with elements to form hydrides and a large number of covalent compounds. And although hydrogen resembles both alkali metals and halogens, it differs from them in a number of ways. Firstly, let us look how alkali metals and hydrogen differ. Alkali metals have very low ionization enthalpy values because it is possible to remove the most loosely bound electron from an atom of alkali metal by supplying very less amount of energy. Okay, but hydrogen has a very high ionization enthalpy value. Its value is 1312 kilojoules per mole like halogens. Because hydrogen has only one electron which is very close to its nucleus. There is strong force of attraction between the nucleus and the electron of hydrogen atom. And removal of such an electron, that would require a very high amount of energy, and for this reason hydrogen has a very high ionization enthalpy value. Clear? Alkali metals can exist in the monoatomic state, but hydrogen can exist only as a diatomic molecule in nature. So this is how hydrogen differs from alkali metals. There's one more difference between hydrogen and alkali metals. While alkali metals are all metals as their name itself would suggest, hydrogen is a non-metal like halogens. For this reason, it never shows metallic characteristics under normal conditions, but hydrogen behaves like a non-metal. Clear? Now, hydrogen differs from halogens in its reactivity. How? While halogens exhibit high reactivity, hydrogen shows only low reactivity. So what do we understand from all these? We understand that hydrogen is unique in its behavior. Hydrogen not only resembles alkali metals and halogens in many of its properties, but also differs from both of them in certain other properties. So, for this reason, it is not possible to include hydrogen along with alkali metals of group 1 or with halogens of group 17. Also, note that when an electron is lost by a hydrogen atom, it results in the formation of H+. And look at the size of H+. It is approximately 1.5 into 10 power 3 picometers. And this is extremely small when compared to normal atomic or ionic sizes of 50 to 200 picometers. As a result, hydrogen never exists freely in nature. Clear? For this reason, it is always found associated with other atoms or molecules. Clear? In the sense, it exists as a diatomic molecule, H2, in nature. So, the position of hydrogen in the periodic table is controversial, and hence it is placed separately in the periodic table. I will now move on to the next important topic of this chapter, which is dihydrogen. Dihydrogen is the most abundant element in the universe. Clear? That is 70% of the total mass of universe is composed of dihydrogen. So which is the most abundant element? Hydrogen is the most abundant element in our universe. It is the principal element in the solar atmosphere that we just saw. Giant planets such as Jupiter and Saturn contain mostly hydrogen. In the combined form, it constitutes 15.4% of the Earth's crust and oceans. Clear? This is important. It is also the essential constituent of water, plant and animal tissues, proteins, carbohydrates, hydrides containing hydrocarbons and many other compounds. Note that only 0.15% by mass of hydrogen is there in our atmosphere. Okay, it is not that much available in our atmosphere. Why? Earth does not possess enough gravitational pull to retain the light hydrogen molecules. Clear? Hydrogen molecules are very light, so the gravitational pull of Earth on these light hydrogen molecules is not that enough to retain them in our atmosphere, and that is why only 0.15% by mass of dihydrogen is there in our atmosphere. Clear? Now, we move on to the next topic, which is isotopes of hydrogen. And before that, we must know what isotopes are. Isotopes are different atoms of the same element with same atomic number but different mass numbers. Okay, isotopes of an element have equal number of protons and electrons, but the number of neutrons in them will not be equal. Clear? Now, isotopes of hydrogen are three in number. They are protium, deuterium, and tritium. Here, protium can be represented as 1H1. Here, the subscript 1 stands for atomic number and the superscript 1 stands for mass number. Deuterium can also be represented as 1H2, where 1 is the atomic number and 2 is the mass number. Okay, it can also be represented as capital D. Okay, not small d. Note that, students. It is capital D. Okay, now tritium can be represented as 1H3, where 1 is the atomic number and 3 is the mass number. It can also be represented as capital T. Clear? Now, what is mass number? We know what atomic number is. 1 is the atomic number of hydrogen. And since all these are isotopes of hydrogen, they all get this atomic number as 1. Okay. Now, what is mass number? It is the total of the number of protons and the number of neutrons in an atom. If you take protium, the nucleus of protium has one proton, but it has no neutrons. So, what did I tell you? What is mass number? It is the sum of the number of protons and neutrons in an atom. Okay, so if you take 1 plus 0, you get 1 as the answer. So, the mass number of protium is 1. Now, look at deuterium. Its mass number is 2. Mass number is nothing but the sum of number of protons and number of neutrons in the nucleus of deuterium. Okay, in the nucleus of deuterium, we have one proton and one neutron. So, the sum of both will give you 2. So, that's how you get 2 as the mass number of deuterium. If you take tritium, its nucleus has one proton and 2 neutrons. So, the sum of 1 and 2 gives you 3, which is the mass number of tritium. Clear? Now, Harold C. Urey, an American scientist, got Nobel Prize for isolating deuterium from hydrogen by physical methods in the year 1934. This is just for your information. I will now explain about the relative abundance of hydrogen isotopes. Which is the most abundant isotope of hydrogen? It is protium. It occurs in natural hydrogen to an extent of 99.985%. And the remaining 0.0156% of natural hydrogen is deuterium. Clear? It occurs in the form of HD. Deuterium occurs in the form of HD. Now, tritium is a very unstable isotope of hydrogen. Why? Due to its radioactive nature. So, let me ask you this question. Why is tritium unstable? It is unstable due to its radioactive nature. Clear? It occurs only in trace amounts. See, there would be one atom of tritium in every 10 power 18 atoms of protium. Tritium emits low energy beta particles and tritium has a half-life period of 12.33 years. Clear? Now, this is all about the relative abundance of protium, deuterium and tritium in natural hydrogen. Now look at the nucleus of protium. It has one proton and 0 neutrons. Nucleus of deuterium has one proton and 1 neutron. And nucleus of tritium has one proton and 2 neutrons. So the nucleus of which isotope has no neutron? Protium has no neutron in its nucleus. Clear? Now, if you look at these isotopes, if you look at the nucleus of these isotopes, you will find that they have same number of protons, but they differ only by neutron number. Clear? Now, what about the chemical properties of the three isotopes of hydrogen? Since the three isotopes of hydrogen have same electronic configuration, they exhibit similar chemical properties. Clear? The isotopes of hydrogen have different bond dissociation enthalpies. See, protium isotope has a different bond dissociation enthalpy than deuterium. A different amount of energy is required to break the bond in protium, deuterium and tritium molecules. Clear? For this reason, isotopes of hydrogen differ in their rates of reaction. And this is an important point, students. Note this. Why do isotopes of hydrogen differ in their rates of reactions? Because they have different bond dissociation enthalpies. Clear? Also, due to different masses, the physical properties of these isotopes are different. Therefore, though isotopes of hydrogen exhibit similar chemical properties, they differ in their physical properties and rates of reactions. This type of difference in properties due to difference in atomic masses is called isotope effect. This is very important, students. You need to learn this. And now we move on to the next important topic in this chapter, which is hydrates. Okay, this is a short question in your exam. You can expect a question on hydrates. Hydrogen, under certain reaction conditions, combines with almost all elements except noble gases to form binary compounds. And what is a binary compound? A compound which is composed of only two elements is called a binary compound. In the binary compound formed by hydrogen, one of the two elements would be hydrogen while the other would be an atom of another different element. For this reason, binary compounds of hydrogen with other elements are called hydrides. Clear? So what are hydrides? Hydrides are nothing but binary compounds of hydrogen with other elements. Clear? This is very important. You need to learn this. How are hydrides represented? You can represent hydrides as EHX or as EMHN. In EHX representation, E stands for symbol of an element and X denotes the number of atoms of hydrogen. Clear? An example of a hydride with EHX representation is magnesium hydride, MgH2. Hydrides can also be represented as EMHN. Here E represents symbol of an element and H is hydrogen atom. M stands for the number of atoms of the element and N stands for the number of atoms of hydrogen. An example of a hydride with EMHN representation is B2H6, which is diborane. Clear? Now, hydrides are classified into three categories based upon their physical and chemical properties. They are ionic or saline hydrides, covalent or molecular hydrides, and the third category is metallic or non-stoichiometric or interstitial hydrides. Firstly, what are ionic hydrides? Stoichiometric compounds formed by hydrogen with most of the S-block elements are called ionic hydrides. What are S-block elements? Elements belonging to group 1 and group 2, that is alkali metals and alkaline earth metals are called S-block elements. When hydrogen combines with S-block elements, it forms stoichiometric compounds called ionic hydrides. They are also called saline hydrides. Okay. Now, some of the examples of ionic hydrides are sodium hydride, potassium hydride, beryllium hydride, magnesium hydride, etc. We move on to the second category of hydrides, which is covalent hydrides or molecular hydrides. What are they? Molecular compounds formed by hydrogen with most of the p-block elements are called covalent hydrides. Some examples are hydrogen chloride, water, methane, phosphine, etc. The third category of hydrides are metallic hydrides. They are also called non-stoichiometric hydrides or interstitial hydrides. Okay, now what are they? They are binary compounds formed by hydrogen with whom? With many of the D and F block elements. Okay, such hydrides are called metallic hydrides. Okay, why are they called metallic hydrides? We know hydrogen combines with elements of D and F block. Okay, D and F block elements are metals. So, hydrides of D and F block elements exhibit properties which are similar to those of their parent metals and hence they are called metallic hydrides. Now, why are they called non-stoichiometric compounds? Okay, let me ask you this question. Which hydrides are called stoichiometric compounds? Ionic hydrides are called stoichiometric compounds. Okay, metallic hydrides are non-stoichiometric compounds. Why? Because the hydrides of D and F block elements are deficient in hydrogen. Okay, their compositions do not correspond to simple whole number ratio. You will understand this when I show you an example of a metallic hydride. Okay, now why are they called interstitial hydrides? Look at this picture. Imagine these circles as metal atoms. Okay, and imagine this red circle as hydrogen atom. Okay, earlier it was thought that in metallic hydrides, hydrogen atoms being small in size, they occupy some of the interstitial sites. Okay, what are interstitial sites? Interstitial sites are nothing but spaces or holes between metal atoms in their crystal structure. Okay, so earlier it was thought that in metallic hydrides, hydrogen atoms occupy some of the interstitial sites, and due to their presence, what happens to the structure of metallic hydrides? It undergoes a distortion, in other words deformation, without any change in its type. That is why they are called interstitial hydrides. Okay, metallic hydrides are also called interstitial hydrides because their crystal structure undergoes distortion or deformation due to the presence of hydrogen atom in the interstitial sites. Okay, and this does not change its type, only its structure is changed. Okay, that is why metallic hydrides are also called interstitial hydrides. However, recent studies have shown that except nickel hydride, palladium hydride, cerium hydride, and actinium hydride, other metallic hydrides have a crystal structure different from that of their parent metals' crystal structure. The examples of metallic hydrides are shown here, and you can see that they are non-stoichiometric. Why? Because they are deficient in hydrogen. If you look at the chemical formula of these hydrides, you can see that their compositions do not correspond to simple whole number ratio. Now, if you look at the chemical formula of lanthanum hydride, which is LaH 2.87, what do you understand? It means that the ratio of the number of lanthanum atoms to the number of hydrogen atoms is 1:2.87, which is due to the defect in the crystal structure of lanthanum hydride. Now we move on to the properties of ionic hydrides. Ionic hydrides are crystalline in nature. They are non-volatile and they do not conduct electricity in solid state. However, in molten state, ionic hydrides conduct electricity. Now, let us understand what happens during the electrolysis of molten ionic hydrides. Okay, now here I have taken the example of the electrolysis of sodium hydride in its molten form. Okay, when electricity is passed through molten sodium hydride, hydrogen gas would be liberated at the anode. See, the positively charged sodium ions would migrate to the surface of the negatively charged electrode, which is cathode, and get discharged. And the negatively charged hydride ions would migrate to the surface of the positively charged anode, and they get discharged, which in turn gets liberated as hydrogen gas. This confirms the existence of hydride ions, H minus ions. Okay, and the corresponding reactions are shown here. Now, what about the properties of covalent hydrides? They are volatile compounds. Okay, now if you take metallic hydrides, they conduct heat and electricity, but not as efficiently as their parent metals do. So, which hydrides do not conduct electricity? Ionic hydrides do not conduct electricity. And which hydrides conduct heat? Metallic hydrides conduct heat. They also conduct electricity. Okay. Ionic hydrides exhibit some more properties. See, lighter metal hydrides like lithium hydride, beryllium hydride, and magnesium hydride. They are ionic, but they have significant covalent character. Okay, beryllium hydride and magnesium hydride are polymeric in their structure. Now, how do ionic hydrides react with water? Here I have shown the example of sodium hydride. Okay, sodium hydride reacts with water violently, producing hydrogen gas and sodium hydroxide solution. Okay, now what about reaction with oxygen or chlorine? Here I have taken the example of lithium hydride, which is a lighter metal hydride. Okay, lithium hydride is unstable at moderate temperatures in the presence of oxygen or in the presence of chlorine. For this reason, it is used in the synthesis of other useful hydrides. Okay, lithium hydride reacts with aluminum chloride in the presence of oxygen to give lithium aluminum hydride and lithium chloride. Lithium hydride reacts with diborane to give lithium borohydride. And note that lithium aluminum hydride and lithium borohydride are very important and very good reducing agents, okay, which are of great industrial use. Now I move on to metallic hydrides. Okay, I told you, remember, metallic hydrides are formed when hydrogen combines with metals of D and F block elements. But note that metals of groups 7, 8 and 9, they do not form hydrides at all. Okay, and in group 6, only chromium forms chromium hydride. So the region of periodic table from group 7 to 9 is called hydride gap, as the metals of these groups do not form hydrides. Okay, now what about the uses of metallic hydrides? Transition metals absorb hydrogen. So their hydrides can be used as reducing agents in the catalytic reduction or hydrogenation reactions of various organic compounds. Okay, now metals like palladium and platinum and so on, there are certain other metals, they can store a very large volume of hydrogen. For this reason, hydrides of those metals, palladium, platinum and all, no, they are used in hydrogen storage and as a source of energy. Covalent or molecular hydrides. They are further classified as electron-deficient hydrides, electron-precise hydrides, and electron-rich hydrides based on the relative numbers of electrons and bonds in their Lewis structures. Now, electron-deficient hydrides have too few electrons for writing their conventional Lewis structures. Electron-precise hydrides have exact number of electrons for writing their conventional Lewis structures. Electron-rich hydrides have excess electrons, that is more electrons than required for writing their conventional Lewis structures, and so these excess electrons are present as lone pairs in their Lewis structures. Group 13 hydrides are called electron-deficient hydrides, group 14 hydrides are called electron-precise hydrides, and group 15, 16, 17 hydrides are called electron-rich hydrides. Now, why do we call group 13 hydrides as electron-deficient hydrides? Because they do not have sufficient number of electrons to form normal covalent bonds, and that's why we call them as electron-deficient hydrides. Okay, now look at electron-precise hydrides. They have exact number of electrons to form normal covalent bonds, and hence we call them electron-precise hydrides. If you take electron-rich hydrides, they have more electrons than required to form normal covalent bonds, and hence it gets its name. Okay, an example for an electron-deficient hydride is diborane, B2H6. Examples for electron-precise hydrides are methane, silicon hydride, germanium hydride, and so on. Okay, you can also write the general formula of alkane, that is CnH2n plus 2 instead of methane. Okay, and note that hydrides of group 14 are all of tetrahedral geometry. They have tetrahedral geometry. Okay, now the examples of electron-rich hydrides are ammonia, water, hydrogen fluoride, hydrogen chloride, hydrogen sulfide, and so on. When you studied chapter 4, you would have learnt about hydrogen bonding. When hydrogen is bonded to one of the highly electronegative atoms, that is nitrogen, oxygen, or fluorine, it involves in hydrogen bonding. Presence of lone pairs on these highly electronegative atoms, that is nitrogen, oxygen, and fluorine, they favor the formation of hydrogen bonds in hydride molecules, and this leads to association of those molecules through hydrogen bonds. One more thing I would like to say about electron-deficient hydrides is that they act as Lewis acids. Okay, Lewis acids are electron acceptors. We know electron-deficient hydrides do not have sufficient number of electrons to form covalent bonds. That's why they are good electron acceptors. Okay, so they act as Lewis acids. Electron-rich hydrides act as Lewis bases because they have excess electrons in them. Okay, they can donate these excess electrons to electron-deficient molecules. So they can act as electron donors. Clear? So electron-rich hydrides act as Lewis bases and Lewis bases are electron donors. Electron-deficient hydrides can act as Lewis acids. Clear? They are electron acceptors. The next topic is heavy water. The chemical formula of heavy water is D2O. Ordinary water contains very trace quantities of D2O. That is, 1 part of heavy water would be there in every 6,000 parts of ordinary water. Now, how is it prepared? It is prepared by exhaustive hydrolysis of water. Exhaustive in the sense, if you carry out the hydrolysis of water for a prolonged time period until only a small volume of water remained, then almost pure heavy water would be obtained. In India, heavy water is manufactured at Baba Atomic Research Center, Trombay in Mumbai by electrolysis of ordinary water. Secondly, heavy water is also produced as a byproduct in some fertilizer industries. What are the properties of heavy water? Heavy water is chemically similar to ordinary water as both hydrogen and deuterium contain the same number of protons and electrons. Clear? So chemically it is similar to ordinary water. However, heavy water has higher density, melting and boiling points than ordinary water. What are the uses of heavy water? Heavy water is used for the preparation of other deuterium compounds. See, calcium carbide reacts with heavy water to give deuteroethane and calcium deuteroxide. Sulfur trioxide reacts with heavy water to give deuterosulfuric acid. Aluminium carbide reacts with heavy water to give deuteromethane and aluminium deuteroxide. So, these are some of the deuterium compounds manufactured by the reaction of heavy water with other important compounds. It is extensively used as a moderator in nuclear reactors, since it slows down the fast-moving neutrons and thus helps in controlling nuclear reactions. You will study about this later, children. And then it is used in exchange reactions for the study of reaction mechanism. What do you mean by reaction mechanism? It tells you how a reaction proceeds, the pathways in which a reaction proceeds. So it can be used as a tracer compound to study the pathways in which a reaction may proceed. So these are all the uses of heavy water. Students, in this video, I explained about hydrogen, its position in the periodic table, its occurrence, about its isotopes, about hydrides, and about heavy water. In the next video, I'll explain in detail about water, about hard and soft water, and about hydrogen economy. So with this, I wind up the first part of my video on Chapter 9, Hydrogen. Thank you for watching.